Hi, I'm Rosario Giustolisi. This is joint work with Mariam Sheikhi Garjan and Kasta Schumann. I'm going to talk about thwarting last-minute voter coercion. So, internet-based voting eliminates the need for physical polling station and allows voters to cast ballots from their laptops. This method promises several benefits, but also introduces challenges that need to be addressed to ensure vote privacy and verifiability. So, vote privacy means that no one knows how an individual voted. But internet-based voting also sometimes offers receipt freeness, which prevents voters from proving to others how they voted, which helps, for instance, to avoid vote buying. So one of the main challenges within internet-based voting is ensuring coercion resistance. Coercion resistance means that no one knows how eventually a voter voted, even if the voter is observed while casting their vote. Coercion resistance is a strong security property, and an internet voting system should provide it together with verifiability guarantees. So there exist several cryptographic voting schemes that address coercion resistance, and normally they use one of these two approaches, fake credentials or deniable revoting. In fake credentials, a trusted registration authority generates voting credentials for the voters during the registration. Voters can create fake credentials that can be given to coercers. In deniable revoting, a voter can cast a ballot during the voting phase that cancels previously ballots cast while being coerced. There are pros and cons with these approaches. In fake credentials, for example, we have to assume the trusted registration authority and that a voter are not coerced during registration. Moreover, we have to assume that there exists a trusted device that stores and hides the cryptographic key related to the credentials. In deniable revoting, for example, we have to assume that a voter can revote after being coerced. That is, we cannot guarantee last-minute coercion resistance. So in this work, we present a new technique that provides last-minute coercion resistance for deniable revoting, increasing the number of advantages provided by deniable revoting. So the underlying idea is to mix fake credentials with deniable revoting by introducing dynamic credentials. With dynamic credentials, the voter credentials changes according to the voter behavior at the voting phase, which allows us to get rid of the classic static credential provided by trusted registration authority. In fact, we don't need any more assumptions like trusting the registration authority or having coercion-free registration. So to make the dynamic credential more robust and obscure the real votes, we introduce the noise ballots, which are cast by a voting server. Now I'm going to provide full details in shortly. So for each voter, the bulletin board publishes a cast ballot record, CBR, which is a list of ballots associated with the voter. In this example, we have the CBR for 4 voters. At registration, a registration ballot, which includes the voter's public credentials, initializes the voter CBR. An authority or the voter themselves can cast such a ballot. Note that the voter can even be coerced at the registration and can reveal the content of the registration ballot to the coercer without the need of lying. So now let's focus on the first CBR, that is the one for voter 0. So during the voting phase, the CBR is continuously populated with ballots generated either by the voter or by the voting server. We require that the noise ballots generated by the voting server are indistinguishable from the voter ballots. In particular, the voting server periodically casts noise ballots that are indistinguishable from the voter ballots and serve to obfuscate the voter's casting behavior and guarantee deniable vote updating to the voter. Each ballot is essentially an Elgamal encryption. A noise ballot is a randomization of this Elgamal encryption. So in the example, the arrow indicates which ballot is being randomized. The key idea behind our technique is that the voter can eventually signal to the voting server which ballots are cast by the voter while being coerced. To do so, voter and voting server keep track of a list of indexes that refers to the voter's CBR. The list contains the indexes of the ballots cast by the voter according to their CBR. Thus, when the voter casts a ballot, this also includes an encryption of the list of indexes. So in the example, the voter cast a ballot for candidate 1. In green, we indicate ballots that are cast by the voter while not being coerced. In this case, this is the first ballot cast by the voter, so the list of indexes is empty. So this prompts the voting server to re-randomize the ballot cast by the voter. Now that the voter cast a ballot while now we consider a voter that cast a ballot while being coerced, and is the one in red. The voter provides an incorrect list of indexes while being coerced. In this case, the set is empty again. So this prompts the voting server to add a noise ballot that cancels the ballot cast under coercion. This is possible because voter and voting server are the only two entities who exactly know which ballots in the voter CBR are cast under coercion and which one are not. In the example, the noise ballot re-randomized the second last ballot in the voter CBR. So at the end, the last ballot of the voter CBR contains the vote that should be counted in the tally. In this example, the voter evaded last-minute coercion attempt. Let's focus on the second CBR. In this case, the voter is coerced at the beginning. So this prompts the voting server to re-randomize the ballot cast under coercion. However, the voter can cancel that ballot by revoting. In this case, the voter provides the index that refers to the ballot cast while being coerced, which is 1. This prompts the voting server to re-randomize the last ballot. So our technique can also allow for coercion and revoting. So let's focus on the CBR for voter 3. Here there is an attempt of coercion. Voter 3 voted for candidate 1, and then later the coerced wanted to cast a ballot for candidate 2, but this attempt was unsuccessful. So now let's assume that the voter changed their mind and now they want to cast a null ballot. The voter can do so by casting a new ballot that encrypts the indexes 1 and 3, which refer to the previous ballots cast by the voter. So at the end, the CBR of voter 3 will contain a noise ballot that encrypts the null ballot. So finally, we show that the last CBR is an example of vote abstention. For tallying, we consider the last noise ballot in each CBR. This allows us for a very efficient tallying that is linear to the number of voters and not ballots. In fact, the trick here is that we can cancel coerced and revoting ballots already at the voting phase. Our dynamic credentials are the list of indexes. However, a voter and a voting server can keep track of them. So now we show how one can encode a list of indexes so that it can be consistently updated as soon as new ballots are included in the voter CBR. So let's consider this example. Here we have an ongoing voting phase and a voter CBR. It now already includes 2 noise ballots and a ballot cast by a voter. So we first associate to each ballot in the CBR a 0 if the ballot is a randomization by the voting server, a noise ballot, and a 1 if the ballot is generated by the voter. So now the given binary value is then stored as a decimal value in the list of indexes of the voting server. If a new ballot randomization is added to the CBR, then the list of indexes is updated to, in this case, 0010. That is, the value of the list of indexes is twice as the previous value. This is because we just expanded the bit representation by 1 element, that is 0. Instead, if the new ballot is cast by a voter, in this case is cast while being coerced, the new value is set 2 times the previous ballot plus 1. This is due to the binary encoding, and in this case the new value is 5. So indeed we added a 1 in the previous one. So if the voter revotes, such as in the case in which they are changing their vote to the null vote, the value of the list of indexes should consider the ballot cast at index 2 and 4. Therefore, the new value is 21. So the voting server checks that the values provided by the voter is correct and randomizes the last ballot. So in this is 21 here, 21 here. There is a match. So the voting server randomized the previous ballot. So for the voter, the ballots consist of 3 El-Gamal encryptions that include the encryption of the vote here, the re-encryption of the list of indexes value here, and the re-encryption of the previous ballot list of indexes value, which is as twice plus 1. For the voting server is also as 3 El-Gamal encryption, which actually are 3 re-encryption. The encryption of the vote ballot depends on whether the provided list of indexes is correct or not, here or here. If so, the voting server re-encrypts the last ballot. Otherwise, it re-encrypts the second last ballot. The other 2 re-encryption sets the values of the list of indexes to the twice of the previous value. So, verifiability of the voting server is guaranteed by a disjunctly non-interactive zero-knowledge proof of knowledge. This means that the voting server doesn't need to be trusted for verifiability. So our proof takes in encryption of both values of the list of indexes, which are publicly available in the bulletin board. This ensures the correct operation of the voting server without revealing the content of the list of indexes. Our technique allows us to define a quantitative measure of coercion resistance, which illustrates that it protects against a brute force attack perpetrated by the coercer. In such a scenario, the coercer may attempt to guess the correct list of indexes by asking the voter to submit several ballots with different lists of indexes. The number of required attempts exhibits exponential growth. Assuming that the CBR contains m ballots, the coercer needs to guess the k out of m ballots. With growing m, it becomes increasingly difficult for the coercer to guess the index list that identifies the complete set of uncoerced ballots. So more precisely, the coercer needs to submit m plus 1th in Fibonacci number. Note that such brute force attack would allow the coercer to update any previously cast votes, but it does not help the coercer to guess whether the voter followed the coercer structure or not. As a successful brute force attack against a vote CBR would require that the coercer casts several incorrect ballots. While this is doable in principle, it is noticeable to the voting server, which can eventually refuse to add ballots at all and block such an attack. Unless the coercer has given different instruction to the voter, the latter just tells the coercer that they have not voted yet. Even if the coercer instructs the voter to vote at certain times, the coercer's chances of guessing the correct indexes are small because the probability distribution determining the time to add the ballots to the bulletin board is chosen by the voting server and not by the voter. So we implemented a prototype of our technique in Python, and ballot generation and obfuscation for 2 candidates requires less than 10 milliseconds, while ballot verification requires less than 1 milliseconds. But most importantly, tallying is very efficient. Now, considering 1 million voters, tallying can be done in less than a minute in a laptop machine. So, in conclusion, we propose the first technique for deniable vote updating that can also evade last-minute voter coercion, which is normally ruled out by state-of-the-art voting scheme that support revoting. Now, our technique can be seen as a mix of fake credential and deniable revoting approaches. It does not necessarily need a filtering phase removing noise ballots, therefore tallying can be very efficient. Thank you for watching this presentation.